Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on osmotic pressure. In our last lesson, we learned about freezing point depression. It is the freezing point of a pure solvent minus the freezing point of a solution. We learned about what happens to the freezing point of a solvent when a certain amount of solute is added. We also learned how to calculate the freezing point depression as well as the freezing point. In today's lesson, we will define osmosis and the osmotic pressure of a solution. We will also learn how to calculate the osmotic pressure of a solution. If you are ready, we will start. Osmosis is the selective passage of solvent molecules through a porous or semi-permeable membrane from a dilute to a more concentrated solution. It can also be the passage of solvent molecules from the solvent side of a solution into the solution side. Students, in image A of this diagram, there are two solutions that are on equal level. As you can see, the two solutions are separated by a semi-permeable membrane. In image B, you can see that the solvent molecules are moving through the membrane from the left side to the right side. This movement causes a shift in the liquid levels in the two arms. Eventually, this difference in pressure will become so large that the net flow of solvent molecules will stop. Students, how else can the osmosis of solvent molecules be prevented? Pressure could be applied to the right arm, as you see here. This would stop the net flow of solvent in either direction. The pressure that is required to prevent osmosis is known as the osmotic pressure, pi of the solution. Dutch physical and organic chemist Jacobus Henricus van 't Hoff discovered that osmotic pressure obeys a law that is similar to the ideal gas law. V represents the volume of the solution. N is the number of moles of solute. R is the ideal gas constant. And T represents the temperature on the Kelvin scale. From this equation, we can write this, in which M represents the molarity of the solution. Students, so far we have learned about two terms, osmosis and osmotic pressure. In a moment, you will see several sentences regarding these terms. However, a few words will be missing. Please fill in the missing words to complete the sentences.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello, everyone. Let us fill in the blanks together. Osmosis is the selective passage of solvent molecules through a porous membrane. You may have also said a semi-permeable membrane. Both answers are correct. The pressure required to prevent osmosis is known as the osmotic pressure, pi, of the solution. Jacobus Henricus van 't Hoff found that the osmotic pressure obeys a law similar to the ideal gas law. Let us continue. Osmotic pressure is a colligative property. Like the other colligative properties we have discussed, it can be used to determine the molar or molecular masses of huge molecules, such as proteins and nucleic acids. Let us work through an exercise together. We will determine the osmotic pressure at 17 degrees Celsius of a 150 milliliter aqueous solution containing 1.75 grams of sucrose per 150 milliliters of solution. First, we can use the information we have to calculate the molarity of the solution. The molarity of our solution is 0.034 moles per liter. We can then use the molarity in the equation we learned earlier in this lesson. Therefore, the moles per liter multiplied by the ideal gas constant multiplied by the temperature on the Kelvin scale gives us the answer 0.812 standard atmosphere. Students, now that we have worked through this exercise together, you are ready to try an activity on your own. Please take note of any important information you will need to complete this activity. In an experiment to measure the molar mass of polyethylene, 2.20 grams of polyethylene plastic was dissolved in enough toluene to produce a 100 milliliter solution. Its osmotic pressure at 25 degrees Celsius was measured at 1.10 times 10 to the negative 2 standard atmosphere. Calculate the molar mass of polyethylene.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. Shall we work through the answer together? From the equation, pi equals m times r multiplied by t, we can create the equation m equals pi over r times t. This allows us to determine that 1 liter of solution contains 4.5 times 10 to the power of negative 4 moles of polyethylene. In order to determine how many moles there are in 100 milliliters of polyethylene, we multiply 0.10 liters by 4.5 times 10 to the power of negative 4 moles and divide it by 1 liter. This gives us the answer 4.5 times 10 to the power of negative 5 moles. We can use this to calculate the molar mass of polyethylene. Therefore, 2.20 grams divided by 4.5 times 10 to the negative 5 mole equals the molar mass of polyethylene. Our answer is 4.89 times 10 to the power of 4 grams per mole. Students, if you had trouble with that activity, please review your notes from this lesson and previous lessons. Today, we learned about osmosis and osmotic pressure. We also learned how to calculate the osmotic pressure of a solution. This brings us to the end of our lesson for today. Until next time, thank you, teacher. Thank you, students.